If you've worked with Python projects, you probably know the usual routine. Install Python, create and activate a virtual environment. Install packages with pip, and recapture those packages so you can recreate the environment later. UV brings all of those jobs together in one fast, streamlined tool. It can install and select Python versions, initialize projects, create virtual environments, install, update, and remove packages, resolve and lock dependencies, synchronize and recreate environments, run scripts and project commands, and run Python command line tools in isolated environments. In this tutorial, we'll connect UV to the venv and pip workflows you already know, and then use its modern project workflow to manage an entire Python project. If you're not familiar with venv, you should watch my tutorial on venv first. It teaches some core ideas on virtual environments in general that will be useful here. UV is a standalone Python package and project manager from Astral, written in Rust. Unlike pip or venv, which focus on one part of the workflow, UV brings several parts of everyday Python development under one command. As for the name, Astral says UV was available on PyPi, fits its celestial branding, with possible readings such as ultraviolet or universal, and was short and easy to type. In practical use, it can manage Python versions, create virtual environments, install and remove packages, resolve direct and transitive dependencies, maintain a reproducible lock file, run project commands, and launch Python command line tools in temporary isolated environments. In its modern project workflow, it manages dependencies through pyproject.toml, records the exact resolution in uv.lock, and keeps the environment synchronized. For an existing project, its pip-compatible interface can continue working with requirements.txt, so adopting UV does not mean rebuilding every project at once. You can use the familiar requirements-based workflow where it fits, or use UV's complete project workflow for new work. Astral provides official standalone installers for Linux, macOS, and Windows. On Linux and macOS, you can run the command shown here, and then use uv-, version to verify the installation. Always copy the current command from the official UV documentation rather than relying on an older tutorial, because installation instructions can change. Astral is also available through several operating system package managers. If you already use pipx install UV is another good option. You can install UV with pip, but placing a standalone project manager inside a Python environment is usually less convenient. If you used Astral's standalone installer, UV self-update updates UV. If you installed it through a package manager, use that same package manager to update it. UV and venv are sometimes presented as competing choices, but that is not quite accurate. Venv is one focused tool included with Python. Its job is to create an isolated Python environment. It does not install Python, install packages, resolve dependencies, or create a lock file. For those jobs, the traditional workflow adds pip and a dependency file. UV is installed separately and has a much broader scope. It can install and select Python versions, create virtual environments, manage packages, resolve dependencies, maintain a lock file, and recreate a complete project environment. That does not make venv obsolete. It remains useful, and understanding it helps you understand what UV is managing for you. Most importantly, UV does not replace virtual environments with some different kind of isolation. It normally creates a standard virtual environment named venv. You can still activate that environment with the familiar source command shown here and use it normally in UV project mode. However, manual activation is often unnecessary. When you use UV run, UV finds or creates venv, synchronizes the project environment, and runs your command inside it, so UV reduces the manual steps without removing the isolation. In either workflow, venv is disposable. Do not commit it to Git. Preserve the project's dependency information, and recreate the environment whenever it is needed. There are two distinct ways to use UV, and understanding the difference will make the rest of its commands much easier to follow. The first is familiar mode. This is useful for existing projects built around virtual environments and requirements files, or when you want to keep using the workflow you already know. You create the environment with UV venv, and then use UV pip commands to install packages. Read a requirements file, inspect the environment, freeze its contents, or synchronize it with a requirements file. Although these commands resemble pip, UV does not call pip behind the scenes. The name describes a familiar pip-compatible interface, but UV performs that work itself. The commands in familiar mode operate directly on the virtual environment. You are responsible for maintaining the requirements file and deciding when the environment should be updated. The second option is project mode. You initialize the project with UV init, record dependencies with UV add, run commands with UV run, and recreate or update the environment with UV sync. In this mode, PyProject Toml and UV-lock are part of one project. Both workflows are useful. Familiar mode provides an easy path for existing projects. For new work, project mode provides the more complete UV experience, so that is the workflow we will use for the remainder of this tutorial. Before we move into the terminal demonstration, let's meet the 4 important components of a UV project. They are PyProject, Toml, UV-lock, Python version, and venv. Each component has a different job. If you are using Git or another versioning system, you will want to commit the Toml file, the lock file, and the Python version files with your project commits. Obviously, do not commit the entire venv folder. That should be excluded in .gitignore. PyProject.toml is the human-facing file that describes the project. It contains project metadata, the supported Python version, direct dependencies, development dependency groups, and configuration for UV or other tools. You can edit it directly, but commands such as UV-add and UV-remove will update it for you. UV.lock contains the exact versions UV-resolved for both direct and transitive dependencies. UV manages this file, so you should not edit it manually. You should, however, commit it to Git. The lock file allows the project to be recreated consistently on other machines and supported platforms. .python version records the Python version the project expects. UV uses it when selecting Python and creating the project environment. Finally, .venv is the actual isolated environment. UV creates it automatically when needed, and it contains the project's installed packages because it can be recreated. It is disposable and should not be committed to Git. A simple way to remember the 4 components is PyProject describes, uv.lock resolves, .python version selects, and .venv installs. One reason UV feels simple is that a single command can coordinate several jobs in the background. When we run UV add requests, UV first reads the project's Python and dependency requirements. It selects a compatible installed version of Python, or it can obtain the required version if necessary. UV then resolves requests and any transitive dependencies that requests needs. Before downloading package files, it checks its global cache and reuses suitable files that it has already downloaded or built. Once UV has found a compatible solution, it adds requests as a direct dependency in pyproject.tom and records the exact resolved dependency set in uv.lock. It then creates or updates .venv so the installed environment matches the project. When we enter uv run main.py, UV compares the project metadata with the lock file and checks the environment. If locking or synchronization is needed, UV handles it automatically. It then executes main.py inside the project environment. The important idea is not the internal machinery, it is that UV keeps the project definition, exact dependency resolution, and installed environment working together, while its shared cache helps make repeated operations faster. UV's scope extends beyond managing project dependencies. It can also find and install Python itself. UV Python list shows the versions that are available or already installed. UV Python install 3.12 installs a managed copy of that specific version. UV normally detects and uses an existing compatible Python installation first. If the required version is missing, it can download one automatically. UV can also run Python command line tools without adding them to your project. UVX-pyfiglet followed by hello from UV runs pyfiglet inside its own temporary isolated environment. This is useful for a tool that you need once or only occasionally. For a tool you use regularly, UV-tool install rough creates a persistent isolated environment and places the executable on your path. You can then run rough directly. This persistent tool workflow performs the same general job that many Python users already know from pipx. Before beginning the demonstration, let's make sure that UV is installed. I'll check with the uv - version command. UV command not found indicates that it is not installed on this system. UV can also be installed through operating system package managers, pipx or pip. We're using Astral's official standalone installer because it does not depend on an existing Python environment, and a standalone installation can update itself later with UV self-update. We'll use curl to download the official installation script from Astral and pipe that script through to the shell. You should always obtain the current installation command from the official UV website. The installer downloads the appropriate pre-built UV executables and places them in our user executable directory. Because this terminal was already open before UV was installed, I'll add .local bin to the path for this session. That makes the newly installed command available immediately. Now we can begin the main demonstration by confirming the installed version. We are beginning in an empty directory where 4 demonstration folders will be created. a traditional -project folder, a traditional -restore folder, a modern -project folder, and a modern -restore folder. First, I'll run uv-version. This reads the version information from the standalone UV executable. It does not need Python, a virtual environment, or an activated environment in order to run. We'll begin with a traditional workflow that will be familiar from the venv and pip tutorials. I'll create a directory named traditional project, enter it, and initialize a Git repository. Next, I'll create a .git ignore file. It tells Git to ignore .venv and Python's cache directory. The environment will remain local and will not become part of the repository. Our small main.py program imports requests and prints its installed version. It does not contact a website, so it will give us a simple, reliable test of the environment. Now I'll run uv-venv. UV locates a compatible Python installation and uses it to create a standard virtual environment named .venv. If an appropriate Python version were unavailable, UV could obtain a managed version. At this stage, the environment is isolated but contains none of our project dependencies. The directory listing confirms that .venv now exists. We'll activate it with the same source command used in the venv tutorial. Activation changes the current shell so that Python and other environment commands resolve through .venv. Next, I'll run uv-pip install requests. UV detects the activated environment, resolves requests and its transitive dependencies, and checks its shared cache before downloading anything it needs. It then installs the compatible packages into .venv. Because we are using the pip-compatible interface, this command changes the environment but does not create a lock file or update project metadata. uv-piplist asks UV to inspect the installed package metadata in the active environment and display what it finds. It does not resolve, download, or change any packages. Running main.py confirms that requests can be imported from this environment. Now I'll run uv-pip-freeze and redirect its output into requirements.txt. UV reads the packages that are actually installed and prints their exact versions in requirements file format. The shell performs the redirection into the file. Like pip-freeze, this records both direct and transitive packages, but it does not distinguish between them or perform a new dependency resolution. We can inspect the resulting requirements file and see the complete installed set. Git status shows the files that belong to the project. .venv is absent, and git check and cured confirms that the exclusion came from our .git ignore rule. Finally, I'll deactivate the environment and return to the parent directory. The environment still exists, but our shell is no longer using it. Now we'll simulate receiving this project on another computer. I'll create traditional restore and copy only the Python source file, requirements.txt and .gitignore. We are not copying .venv or the original Git repository. After entering the new directory, I'll initialize a new Git repository. The directory listing confirms that there is no virtual environment here yet. I'll run uv-venv again. UV discovers a compatible Python interpreter and creates a completely new empty .venv. Nothing from the original environment was required or copied. After activating it, I'll run uv-pip sync requirements.txt. UV reads the exact requirements, resolves and validates the complete set, reuses compatible files from its cache, and installs them into the active environment. Sync is stricter than a normal install. It also removes packages that are not listed, making the environment match the requirements file exactly. uv-pip-check now reads the dependency metadata from the installed packages and looks for missing or incompatible requirements. It does not contact a package index or modify the environment. No broken requirements tells us that the restored set is internally consistent. uv-piplist performs another read-only inspection of the active environment. The listed packages should match what we recorded earlier. Running main.py proves that the newly restored environment works. Git status and git check, ignore again, confirm that source and dependency records belong to the project, while the generated environment does not. We can now deactivate this environment and return to the parent directory. The traditional lesson is that the project can be restored from its source files and requirements. .txt.venv remains disposable, just like the traditional venv-pip workflow. Now we'll repeat the complete process using UV's modern project workflow. I'll run uv init --no package modern project. UV creates the project directory, initializes git, and writes main.py pyproject.tom.python version readme and .gitignore. The no package option gives us a simple application with a top-level Python file and no build system. UV does not create .venv or uv.lock yet because no project command has needed them. Inside the project, the directory listing shows the generated structure. .python version reflects the Python version UV selected for this project, .git, Ignore already excludes virtual environments and common generated Python files. PyProject.toml contains the project metadata, supported Python version, and an empty dependency list. Git status confirms that UV initialized the repository and that these are the new project files. For a direct comparison, I'll replace the generated sample program with the same main.py used by the traditional project. Now I'll run UV add requests. UV reads the project's Python requirement, selects a compatible interpreter, and resolves requests together with its transitive dependencies. It reuses cached package files when possible, adds requests as a direct dependency in pyproject.toml, records the exact resolved set in uv.lock, creates .venv, and synchronizes the required packages into it. The directory listing now includes both .venv and uv.lock. PyProject.toml shows requests as a direct dependency, while UV manages the exact version separately in the lock file. UV tree reads the resolved project dependency graph and displays the relationship between direct and transitive packages. Before displaying it, UV checks that the lock file still agrees with the project metadata and updates the lock if necessary. Next, I'll run UV run main.py. UV checks whether pyproject.toml, uv.lock, and .venv are sufficiently up to date. It synchronizes anything required, selects the Python interpreter inside .venv, and runs the program there. We did not activate the environment. Now I'll run uv add --devruf. UV adds ruf to the development dependency group rather than the application's runtime dependencies. It resolves ruf alongside the rest of the project, updates uv.lock, and synchronizes the default development group into -venv. UV run rufcheck.again checks the lock file and environment, locates the ruf executable inside the project environment, and runs it against the current directory. Ruf remains isolated with this project and activation is still unnecessary. Next, I'll run uv-lock --upgrade package requests. UV keeps the project's declared version constraints but allows requests to move to the newest compatible release. It re-resolves any related dependencies that must change and updates uv.lock while retaining other locked versions whenever possible. Because this is a lock command, it updates the resolution record but does not synchronize .venv by itself. If requests is already at the newest permitted version, the lock file may not change. Now I'll run uv remove requests. UV removes requests from the direct dependencies in Py. Project.toml calculates which packages are no longer needed, updates uv.lock, and synchronizes the project environment to match the new dependency set. The updated PyProject file confirms that request is no longer declared. Because our program imports requests, I'll add it again with uv add requests. UV repeats the project workflow. It restores the direct declaration, resolves a compatible set, updates the lock file, reuses its cache where possible, and synchronizes .venv. UV run main.py validates the project state, uses the interpreter in .venv, and executes the program. This confirms that requests is available again. Git status shows pyproject.toml and uv.lock as project files, while git check ignore confirms that .venv remains excluded. Now we'll restore the modern project in a completely separate directory. I'll create modern restore and copy the Python source pyproject.toml uv.lock.python version, .git ignore, and readme. We do not copy .venv or the existing .git directory. After entering the new directory, I'll initialize a fresh Git repository. The listing shows the complete project definition, but no environment. If you really wanted to copy the full Git folder, you can do that, of course. Now I'll run uvsync. UV checks that uv.lock agrees with pyproject.toml, reads the project's expected Python version, and creates a new .venv because one does not exist. It then installs the exact locked runtime dependencies and the default development group, reusing cached artifacts where possible. Sync makes the environment match the selected project dependencies and removes extraneous packages by default. The next directory listing confirms that .venv has been recreated locally. UV run main.py checks the lock file and environment again. Because UV sync has already brought everything up to date, UV can immediately select the environment's Python interpreter and run the program. UV run rufcheck performs the same validation, finds the restored ruf executable in .venv, and runs it without activation. This proves that the development dependency group was restored as well. UV tree checks the project resolution and displays the dependency graph recorded for this restored project. It gives us the same direct and transitive structure we had in modern project. Finally, UV pip check discovers .venv in the current project directory and inspects the installed package metadata for missing or incompatible requirements. It can find the standard .venv even though we never activated it, and it makes no changes during this check. Git status and git check ignore provide the final confirmation. The project definition is preserved and the recreated environment remains disposable. The modern lesson is that pyproject.toml describes what the project needs. uv.lock records the exact resolution and uvsync recreates .vend. The environment itself never needs to be copied. We'll finish with a one-time command line tool. I'll run uvx pyfiglet followed by uvworks. uvx is the convenient alias for uvtoolrun. uv resolves the pyfiglet package, checks its shared cache, obtains anything missing, and runs the command inside a temporary isolated tool environment. That environment is separate from modern restore, so pyfiglet is not added to pyproject.toml uv.lock or the projects.vend. And there is our result. UV works. We have now used UV in both styles. It can accelerate the familiar venv and requirements workflow, or it can manage Python dependencies, locking, synchronization, and command execution as one modern project workflow. The modern UV workflow can be remembered with 5 commands. UV init creates the project. UV add declares a package, resolves its dependencies, updates uv.lock, and synchronizes .venv. UV run checks that the project is current, then runs the command inside that environment. UV lock explicitly refreshes the dependency resolution, and UV sync explicitly makes the environment match it. In everyday use, locking and syncing are usually automatic. 3. Supporting commands round out the workflow. UV remove updates the project when a dependency is removed. UV tree displays the direct and transitive dependencies. And UVX runs a tool in a separate, temporary environment without adding it to the project. The key is that UV still uses a real virtual environment. UV run simply makes activation optional. pyproject.toml declares the project and its direct dependencies. uv.lock records the complete resolved environment, while .venv remains disposable. Keep the project files and recreate .venv whenever necessary. And remember, UV pip supports traditional requirements .txt workflows, while UV can also manage Python versions. Which workflow should you choose? Use venv and pip while learning the underlying Python tools, or when you deliberately want a traditional workflow. For an existing requirements.txt project, UV, venv, and UV pip provide a faster, familiar approach with UV performing the work. For a new project, use UV init, UV add, UV run, and UV sync. My recommendation is simple: learn what virtual environments do. Then let UV automate the repetitive parts. I really enjoyed making this tutorial. I hope you enjoyed watching it. For a deeper look at the foundations behind UV, watch my virtual environments tutorial and my pip tutorial next. They explain environment isolation and package management in more detail. If this tutorial helped, please like and subscribe. That really helps. You will also find some recommended Python books in the description. Thanks for watching.